I'm already live, baby.
Put it on this box.
What?
Put it up a little so that it's like...
Oh, and it's fine. Nobody cares what I look like. Which is true. Alright. Hey, everybody. Oh, I should switch it to me. Switch it to me face. Hello. Alright, so I'm going to be going over this bonus hour for the weird times that we're in. I'm going to be doing a run through of the project. Not the whole thing. We're mostly going to focus on the binary search tree, which is worth 70% of the project grade. It's worth the majority of the project grade. And it'll probably be most of the effort you put into the project. So yeah. Photoshop. And at the end of this, I'm going to hop in the Discord, and then you guys can ask me questions while I'm doing this, and then I can answer them. So let me go to Photoshop. Let me see. Okay. Yes. All right, cool. So I'm still getting used to my pen thing, but I think I have a better solution. It's Project 3. All right. So Project 3 is a tree of trees. So what you're going to have is you're going to have a binary search tree like this. And then this whole thing is going to be a node in like a big mama binary search tree, right? There's going to be another node down here with like a smaller thing. And then there's going to be another node, like, right? So that's kind of what this is going to look like at the end of the day when you're done everything. Now, the outer, the big honka-jonka binary search tree is a splay tree, which, if you're in my lecture, we have not covered splay trees. I will probably release a video next week, or I'll cover it at the beginning of Monday's class. We'll talk a little bit about splay trees. But the splay tree is the outer tree here. And so what we're going to talk about today, this thing is worth 30% of your grade. We're going to talk about the binary search tree that's in here. And this is a balanced binary search tree. Splay trees are as well, but they're a little wonkadoodle in how they balance themselves. I'm also not looking at chat yet, but I'll look later. I'm going to kind of just straight out lecture and then take clarification questions. This is a binary balanced binary search tree, and we're going to use arrays to balance it. And this is worth 70% of your project grade. Both the tests that you write for it and your actual implementation of it. So for this session, I'm just going to talk about this sort of like inner tree in here, and we're going to leave the outer splay tree for later because it's probably going to be tricksy enough with what am I doing here? It's going to be tricksy enough to get that inner tree working correctly. Okay. So, your node has two values in it. There is a string and there is an int. The int is our key, and that means that's what we're going to be sorting the tree on. So, So what that means is, when we do our binary search tree, if I have a node that's 5, and I'm trying to insert 17, that means I'm going to go down the right tree. And the things that I'm comparing here, this 17 and this 5, are the keys for those things. So what that means is the binary search tree, in terms of how it's sorted and how it's structured, does not care about the strings. It only cares about these integers here. So that's that. Boop. Okay. So, how do these work? So they're normal binary search trees, except there's two main things I want to talk about, which is function pointers and then the array-based rebalance. Jules, behave yourself. Okay, so let's talk about how the tree restructures it first. So we have a tree like this, and we'll put a node down here, and a node here, and a node here, and a node here, and a node here. So after I insert, let's use, so there's a bunch of different ways you can determine whether or not a tree is imbalanced. The one that AVL trees use, their height balance property, looks at the height of each subtree, and if its difference is greater than 1, it will say that that node is imbalanced and requires a balancing operation. So there are other ways to do it. You could say if the size, meaning how many nodes are in the left or right subtree, gets out of whack by a certain amount, you can do a whole bunch of different things. But we're going to be looking at, for this example, height. The actual function that determines whether or not a node is imbalanced will be supplied by the user in your code, which by way of a function pointer, which is weird. You've probably seen something, it's like barfle, biffle, boofle. What is it? It's hold on, I gotta find the name of this. So the name of the function pointer type is Baffled. We're gonna say Baffled. Lord Baffled. And that's a function pointer. So let's just assume that you have a function called Baffled. That isn't quite 100% true, but it's close enough, and I'll get into that in more detail. But this balance function, you're going to call it with a pair of heights and a pair of sizes representing the left and right heights and sizes, and then it'll return true or false. True if the tree is balanced and false otherwise. Or maybe the opposite of that, I forget. It's in the project description. Anyway, so say I just inserted this node down here at the bottom. You don't have to write anything but an insert for this project. Wow! Incredible! You should be relieved. Because, as you may have followed from the red-black tree lecture I just gave you, removes are pain. Though I don't know if they'd really be a pain for this. Anyway, so what we're going to do, remember what we do in AVL trees, is we look for our imbalanced ancestor. And so what we do is we walk back up the tree until we find a node that is imbalanced. And the way that we determine whether a node is imbalanced is we call this Baffled function on it, which will be described in the, which will be saved as a private member variable named _imbalanced. So you're going to have a function. So your function pointer, we'll put it down here, is going to be imbalanced. So you're going to call imbalanced on each of these nodes as you go back up the tree. And if any of them says that they're imbalanced, so I guess it returns true if they're imbalanced with a name like imbalanced. It must be true if they're imbalanced. So using the AVL tree height criteria, let me delete some of this silliness. That is not a delete. Oh, it is. I need to make that pen size bigger for this. Oh wow, that just straight up didn't work. Still getting better at this. Size, big. Still not big enough size. Bigger. Now we're talking. Now we're cooking with gas. I came here to learn about trees, and it's just my professor messing around with Photoshop. Look, we do our best. What is this? I'm not using the right tool at all, am I? What is this? It's the spot healing tool, damn it. hope Min's not watching this. Okay. So we're going to call the imbalance function on each of these. If we're using AVL rules, if we're using AVL tree rules, will this one be imbalanced? Why am I red now? What did I do? How did I do that? Okay. Will this one be imbalanced? No, it's balanced because I've got one child down here and no children, so that's balanced. Will this one be imbalanced? Well, I have 2 on the right-hand side and 1 on the left-hand side as far as height's concerned, so this one won't be imbalanced. But I come up here and I'm going to have a height of 3 on the left-hand side and a height of 1 on the other side, which is problematic. So I need to call the rebalance method. So you should write your own rebalance method. And the point, what the rebalance method is going to do is it's going to give you a new subtree at that root. Whoa, what just happened? So it's going to replace this entire subtree with a new subtree that's more balanced. Okay. I'm going to go look at the chat now, see if any of you are chatting up in the chat stream, and see if there's any questions thus far. There's only 11 of you. All right, cool. Oh, Abel is in the thing. Abel, do you have a question? Or Abel? Abel. I can never get it right. I'm terrible. All right, I'm going to disconnect from Discord so that you don't hear me twice. Okay. All right, so we're gonna go to the next situation here. New. Okay, so let's draw a tree that I'm gonna. We'll do. I think this was more or less the tree that I had, like this, and I'm gonna restructure this, right? So the way that we're going to restructure is we're going to put all of these in sorted order into an array. And I don't believe you're forbidden from putting them into an array or into a vector. So we're going to use a vector because that's much easier. How big the size of the root node that we're going to replace. So we know that we're going to have 6 things in this array, so, or a vector, or whatever you decide to use. But it should probably be a vector. So how do we get these things into a vector? Well, how do I get a binary search tree? How do I get its values in an orderly fashion? So how do I get the ordered contents of a binary search tree? So the way I get the ordered contents is I do an in-order traversal. Where is the lowest value in this tree? Why, it's here. It's here. So this one will go here. And then we follow the in-order traversal. That means this one will go here. And then that means this one will go here. This one will go here. This one will go here. And this one will go here. Also, I should mention there's this, it looks like the sun. This is going to be the former parent of the node of the tree that we're reconstructing. What we want to do is send back to them a pointer to the new root. Okay? So now I have all of my nodes stored in here. What type should this array be? I would recommend it be a of type node pointer. That way you can you don't have to take the values out and reconstruct new nodes. You can just change the nodes that you already have. So now all of my nodes are inside of this array here. And so the question is, how do I reconstruct a balanced tree from a sorted array? Well, a really easy way to get... One thing that we know about array storage for a tree is that when you store a tree in an array, it's a complete tree. And complete trees are nice because they're basically just perfect trees with an extra layer on them. So they're super balanced. So what we're going to do is we're going to write another method that's going to recursively reconstruct the subtree from the contents of this array. So what should the new root of the tree be? So the new root of the tree should be the item in the middle, which should be one of these two. Does it matter which one you pick? I don't think so. So pick one of them. But double check the project description. I don't think it says that you have to pick one or the other. Pick one of these two. And so what I'm going to do, so say I pick the one that's the lower of the two. So I'll just pick the lower one. So I'm going to say that this node that went in here, so right, this node up here is the one that's in that spot. That's going to be the new root. Cool. So now I have my new root. Now, its left child is going to be the root of the tree I build from this array. Build from array. That is going to return me back a node. And the right child of it is going to be the result of calling build from array on the second half of this sorted array. So that's going to return a node. That will be the new right child of this root node. And so what does this feel like? So I'm taking the middle point here, and then I'm doing something with the left-hand side, and I'm doing something with the right-hand side. What does that feel like? That feels like binary search. So basically, a binary search tree, a really well-balanced binary search tree, is basically storing the intermediate results of a binary search. So that's essentially, you're just reconstructing a binary search tree by kind of, you find the new root by looking at the middle item, then the left subtree is going to be repeating the process on the items before it in the array, and the right subtree is going to be repeating the process on this the stuff in the right on the right side of the array. And so ultimately, after this, each recursive call is just going to return its root, right? Because if you return the root and everybody's all like tied up correctly with pointers, then eventually you'll get a root back all the way back that you can send to the old parent of the unbalanced version of this tree. Okay, all right. I'm going to go back and look at Discord. And I'm going to go look at the chat. In order traversal, middle to ends. Yeah, Tim's got it. Okay. So this is how your balancing operation is going to work. So then there's this question of what about this? So we talked about it back here on the previous one. What is the deal with this thing and this thing? What's baffled? Baffled? What is... We didn't learn about baffled in 201, and it's being used by a type, as like a type. So this brings us to the discussion of function pointers. So let me make sure that my C line isn't filled with the project solution. It is. Oops. Stand by. Or at least what I've done of the project solution. Alright, now I'm going to switch over to Selenium. And it's looking at the wrong thing. Cool. Alright. Nice. Look at my hair. It's going to get wilder as our isolation continues. So I'm just going to go... It's a good look for me. Okay. So here we are in the project doing stuff. So I'm going to embiggen. So here's baffled. What? The what? The what is baffled? Baffled? So typedef is a keyword that allows you to define a new type that you want to use somewhere else in your code. So sometimes you'll see typedef BST data type, and then that's just like float or something like that. Wait, what? Did I get it backwards? Unknown type name? Whoops. A BST data or something. So now you could use this anywhere else as if it were a type, and it will work. So then what the actual nightmare realm, like what kind of demon does this line 23 summon? It looks kind of like a function, but there's like a pointer bit in there, and so these are called function pointers, and they're actually pretty rad. They're pretty cool. You don't have to use a typedef to use function pointers. It's just common to use a typedef for function pointers, because otherwise this would just be the type of a thing in your code. Which means what I could do down here is, instead of baffled, I could do bool star, whoops, not 8, star imbalanced, and then grab all of this. Boop. These are equivalent statements. What a function pointer is it's kind of what it sounds like. It's a variable whose value is a function, meaning anywhere in my code, I could come down here and I could write, like, I don't know, height. So BST is best ST. What does it return? Int BST height const. And I could call imbalanced in here. I can call it. Boop. And I'm calling it just like a function. I'm calling it just like a function. And so what this means is, when you're making the binary search tree class, in the constructor, you're giving it a Baffled, which just means I'm giving you a function pointer. The type of the function pointer is it has to be a pointer to a function that returns a Boolean and takes 4 integers. That's what all this, like, rigmarole means, is that you have to have defined a function that returns a bool and takes 4 integers. And that's why the type is so long, is because you have to specify all that information. So if you want to make a BST, so say if we want to make a BST down here, I don't, does BST, so let's make another function. It has to be a bool, right? My balance, that takes int x, int y, int z, int q, and returns true. And then down here, I'm just going to go BST tree, and then I'm going to send it the address of my balance. Ta-da! And then that works. So what that means is, I want to create a binary search tree that calls this function I've written when it tries to determine whether or not a node is balanced or not. And so that's the whole point of function pointers in this project, is to make it so that you can write binary search trees that balance more or less aggressively. And you could like look at the different performances of them. If you wanted to make a really poorly performing tree, you could just make my balance always return false, which means that it will never say that it's imbalanced. And also, if you want to make it a really imbalanced tree, you could have it return true, or really slow tree, you could have it return true, which means that it would always rebalance every time, every node. Gross! Which would make it really slow. So you don't want to do completely one or the other, and so because these are defined as left height and right height, I would switch to the CPP file, but it has my project solution in it. But basically, you would compare the absolute value of the difference between left height and right height and see if it's greater than 1. If it's greater than 1, then you'd say, yeah, this is unbalanced. And you wouldn't even do anything with size. You wouldn't. Be like, AVL trees don't care about size when they're determining whether or not the tree is balanced or not. Whether or not the tree is balanced. Full stop. Okay. All right, I'm going to go back to the streamy strams. It's too low. We can have pointers to function. Is this going to be available to rewatch immediately after I conclude it? Yep. How would the heights and sizes be affected? Affected with an A! Word nerd. Affected with an A is a verb meaning to apply an effect to. Effect means to bring into an existence. Yeah. You're like, that's not what I care about right now. That's okay. It's okay, but it should be. I shouldn't call you out, but... Wait, so is the pointer value the actual function call or the result returned from that function? So here's the crazy thing. The actual pointer value is the address of the function in the memory where the program instructions are stored. So, yeah. When you get, if you're not taking 313, or you might not even get this till 411, you can actually write assembly code that just arbitrarily be like, oh, I have in this register the address of a function. So, yeah. This is comp sci, not English. Yeah. But yeah, so the value of a function pointer is... What's actually stored there is the address of the function, but the way that you use them is you just call them. Whoops. Wait, this is not the right. You just call them. So in this method, you just call imbalanced, because it's a function pointer. Even though it's in your private section, and it acts like a variable in that you can, right? Because the other weird thing is that you're sending this to a function. And again, if I want to be really, if I want to actually not use Baffled, this is what it would look like with Baffled. So when I'm calling that constructor, I'm sending it the address of a function, which is you put the little ampersand in front of a function name. And then that will be stored as a variable inside of the tree. And then you can call that function as if it's a function that was implemented anywhere. Which I mean it is. It's implemented somewhere because you can't give it nothing. Well, you could, and that would be problematic. Other languages, if you guys have done Python, you can do this in Python. This probably won't let me write Python in here, but you can do thing equals lambda x x times 2. Oh, right, it's giving me errors because I'm not in Python. And basically what you're doing is lambda is an anonymous function, and you're storing it into a variable called thing. And if you've ever written JavaScript, JavaScript takes this way too far, and the language is pretty bad because of it. But yeah, function pointers are a thing. And it's actually, the way function pointers are used in the wild, the way you're going to actually practically use them. I mean, this is a practical use of a function pointer, but the place that they're used most commonly is, there's anytime you're doing something asynchronously. So what I mean by that is, say I'm grabbing a bunch of website contents, like downloading a bunch of images. I could send out the request to download one and wait for that to finish and then download the second one. Or I could send all the requests out and then as they come in, handle them. And the way you typically do that is you would write something that said, like, make this request and here's a function pointer to a function that will handle whatever comes back from that request. And so you send them all out. Something either function pointers directly or something similar to function pointers are being used for like mouse clicks. So if you've ever done like Java Swing or any of these other interface, like graphical user interface type things, you'll occasionally, it'll be like, well, in order to get a mouse click, you have to write this class, and in the class you just defined a function mouse click. And I always was like, how does it know to call this? Like, what is magical about mouse click? And it turns out that function pointers are happening. So, good stuff. Explain the balancing algorithm again. Can you go over the BST output and explain what the parentheses for? Bless you. Bless you as well. I know like 5 words, man. That's more than 5 words in that statement. That is 6 words. And you said like. It's a softening. Alright. Alright, go over the BST output. Oh, from the dump. Yeah. Alright, let me go over that. I have to remember how it works. Where's an example? Where's the example? Example? Where is the example? Oh, it's probably here in C-line somewhere. It's driver output? Yeah, it's this thing. Alright, how does this work again? Man, birds are so loud. Don't think it matters. It doesn't matter in terms of like what you output, but also making sense of the sample output is kind of important. But I will talk about this for a second. Bum, 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 bum. So generally how these work are the parentheses are indicating like depth, and these are really hard, like it's making me go back to my Lisp days. And the colon is for left and right subtrees. The parentheses are around each node. Why are there 2 values in them? Oh, because they're the boundaries. That's right. So, oh my gosh, I'm struggling very hard with this. So for the splay tree has 2 boundaries in it. And so each node here, like if I were to write, I think, we could have, if it was a tree, it would just be like 1, 10, 20, 30, 30, or 40, 50. So struggle. I know you guys have been spending. Ooh. You've been spending the past week watching your professors struggle with technology. I'm glad I can continue that proud tradition. All right, it's just gonna have to be in the middle of the screen. Wait, does this work? Can I undo that? How about, is it a layer? It is a layer. How do I move the layer? Can I move the layer? No. Can I move the layer here? Can I unlock the layer? I don't know anything about anything as far as Photoshop's concerned. Move. 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 We did it. Guys, we did it. Oh my gosh. I'm learning. I almost never use the shops. Can I still make the drawings go? Oh my gosh, I can. So what this is if I have a root node, of 20 colon 30, and these are the boundaries of the weights. So what this is saying is there's a binary search tree in here that's lowest value is 20 and its highest value is 30. And then this has a left child that is 1 colon 10 and a right child that is 40 colon 50. And then these guys have null pointers because they don't have anything around them. And so if I were going to add a left child to 40, 50, that was something like 60, 70. I would, how would I change this? I would put like an additional set of parentheses. Or, Steve's gonna watch this and be like, he's so not right. I think you would do. I think you would do something like 60, 70. But you're going to do a tree traversal to generate this tree. Oh no, you would do this. It would be like this, I think. You're going to do a tree traversal to generate this output. So it's going to be an in-order traversal, judging by how these work. You can see these boundaries, like it goes 1 to 34 and then 35 is above that. You're going to do a tree traversal to generate this. You might have to like change where the parentheses live to get it to look exactly like this. But in general, it's printing out the nodes of your tree in their in-order traversal with parentheses to denote where the node boundaries are. Okay. Let's go see if there's any other questions. Can I make dump not const? No, dump should be const. Order cursive order traversal, that's making needs. Why? What are you changing in? Ow, why are you biting my foot? Why? Yeah. Can I make dump not const? No, leave it const. You shouldn't be modifying the tree. Sorry. Okay. Any other questions? My mad hair. My hair. It's crazy. Oh, I didn't show this in Photoshop. My bad. I didn't change the scene. That probably helps. I'm sorry. I'm still bad at this. I'll probably never be good at it, but I can live with that. So, yep, that's there, and that's how that's what that tree looks like. I think that's what that tree looks like. All right, I'm gonna hop into the Discord chat, and if anyone wants to ask me questions with their vocal cords, they're welcome to do so. No, I'm not going over scanner today. Next week. If you got to doing scanner, that's great. You should do the BST first, though. The BST is worth 70% of your grade, and it requires... you need to get it working before scanner will work anyway. At least this is a project where when you're done, you get a pretty picture out of it instead of like a 5. Nobody for Discord? Nobody wants...
Hello, I have a question.
Oh, yeah, go!
So, for the array reconstruction, what happens to the heights again? Like if I completely reconstruct the array, reconstruct the tree, a subtree of the big tree, what happens to the height of part that I didn't construct? Like say I had a little extra part hanging on the bottom that was increasing my height by 1, and when I remade the tree, that part got moved up. How would it affect all the root node at the top?
So after you finish your rebalancing, you're going to have... Well, after you do an insert, you're going to have to update the height up the tree anyway. So you're just going to continue doing that process. So like,
okay.
if I'm a new leaf, then when I get inserted, my parent might have gone up in height, and so like all of my ancestors could have potentially gone up in height. So after every insertion, not just one that caused a rebalance, but after every insertion, when you recurse back up the tree, you're going to have each node check that its height has been up. Check to see if it needs to update its height and do so if it needs to.
Okay. That makes sense.
And then when you're doing the reconstruction, you're going to have to like manage the height there as well. But
and one more sort of general programming type question.
Yep.
The way I'm writing the project is that you have insert functions that return pools. So I'm just making a private insert function that's named slightly differently that I can do recursively.
Mm-hmm.
And I did the same thing for dump, and I did an in-order recursive one for that, but because of the const, it's not making my code work.
What are you changing about the tree, though?
I'm not changing anything. I'm just iterating through it.
Then shouldn't is it just because your recursive function isn't declared const? Is that the problem?
I can try. It'll take me a second to log in so you can answer someone else's question.
Sure. Anybody else?
Can I go now?
You may.
Awesome. Hey, Professor, how's it going?
Hey, Tuba, how's it going?
Pretty good. Okay, so I have like the process written down, how I was thinking I would rebalance it. Could you tell me if this is like a good way to think about it?
Okay.
All right, so I have my BST. I put stuff in it, or I insert stuff in it. Now that I've inserted stuff, every time I insert, I should call my balance function to check if my tree is balanced. That'll then return me a bool. So let's say that it is imbalanced. Now that it's imbalanced, I should, through an in-order traversal of my BST, move it into an array. Now that I'm in that bad boy, I find my middle guy, all right, and that's going to be my new root for wherever that imbalance subtree is in my original BST. Right? Still with me? Am I still good?
Yeah.
Okay. All right. So now I go to my BST. I find that root by finding that key in there. So now I know where it is. And now that I know where it is, I need to delete every node up to that root node to make it a leaf. And now that I've done that, I can then push in the values from the array from left to right and insert them at that root node that I found in the BST. Does that work?
Close, but no. So you're gonna put them in the array, but you're not gonna go left to right, because if you insert them left to right, you'll get like a linked list that just goes all the way to one side, because that's kind of like a worst case tree, right?
Yeah.
So you want it, if you have an array of values, if you have an array of sorted values, which items should be the root of the new tree in order for it to be a balanced tree?
The middle.
Yeah, the middle one, because then half of the nodes will be on the left-hand side and half of the nodes will be on the right-hand side. So basically what you're going to do is you're going to, this is a recursion in your recursion, you're going to have that array, and then you're going to have a recursive function that you send that array, and it gives you back the root of a new tree that it is reconstructed. What that means is you're going to take the array, you're going to pull out the middle node and say, you are the new root. And then you're going to say, for all of the nodes before it in that vector, you're going to say, okay, now reconstruct a tree out of those nodes and give me the root back, and I'm going to make that my left child. And then reconstruct the right side of the tree with the second half of the list. Does that make sense?
Okay. Yeah, okay, wait. Okay, wait. Okay, yes. Okay, wait. Alright, okay. So, just to... Okay.
Did you see the beginning of my stream?
I did not. I missed like the first 10 minutes.
Oh, okay. Well, you can rewind it. I did explain it, but I'm going to do it again, because if it doesn't hurt to repeat yourself when you're explaining things, so...
Awesome.
I'm going to...
So when you say I have the middle, and I need to make them the left side nodes of that middle in the array, a tree in and of itself, what is going to be the root for that tree?
So
is it just binary search again? Like, do we just pull the middle of the left side again?
Exactly, yeah. And it actually ends up, it's like you're running a binary search, and you're just kind of like, you're running a binary search, but you're actually kind of just building a tree in the shape of the binary search that you would be running.
Okay, got it. And then how many times should I go through it?
Well, every time, so when you pick the root is the middle one, you're going to recursive, so you're going to have a function that's like, I give it an array, and it gives me back a root node of a constructed tree for that array. You're running a binary search, but you're actually kind of just building a tree in the shape of a binary search. Oh wait, that's me in the background.
Yeah.
Okay. Now I can't talk over myself. That would be disrespectful. When you pick the root is the middle one, you're gonna recursive. So you're gonna have a function that's like, I give it an array. Wait, who is? Oh, that's Michael. Okay. All right. Sorry, I muted the wrong person. Okay, that really threw me off track. Okay, you're gonna have a function that you give the array to, and it returns back a node pointer, and that pointer is going to be the new root, and it's also going to be the element that's the middle of the array, but that you don't need to care about that. And that's the function you're just going to call recursively. So you pull out the root, and then you call that very same function again with the first half of the array. And you say, hey, make a tree out of this array. It's a smaller array. So when to stop is when that function's been called with an empty array. And you're like, I'm going to return null because there ain't anything in this vector.
Got it. Okay.
Just like how eventually when you're doing a binary search, you'll get to a point where your binary search will be recursively called, and it'll be like, tell me if the item is in between index 0 and 0, and you're like, there aren't any things in between. That's not even a valid thing to ask me. So yeah, that's what you're gonna do. It's just kind of recursively reconstruct the tree from that array.
So when I call that recursive function and it gives me that root node, do I then just pass? So, how do I construct that root node back into my original binary search tree, or am I just making a new tree at that instance and then passing it back into the BST?
Well, so Yeah, you're just you're inside the BST at this point. Like, you're writing methods inside of the BST. Like, this reconstruct tree from a vector is going to be like a private member in your BST. And so you can change, so you said this thing about like deleting all the nodes and all this other stuff. You don't need to delete anybody. Basically, you can just make a vector of node pointers, and then when you pull out the middle node, you're going to say, well, this is the node I'm going to return, and then I'm going to change its left pointer to be the root of performing this operation on the front half of the list, and I'm going to change its right pointer to be building a tree from the second half of the list. And so as a result, you've like recreated the tree. So let me get to drawing.
Oh, okay. So it's a vector of node pointers. Okay, gotcha.
Yeah, it's a vector. That's an easy way to do it. Yeah. So I'm also gonna share in Discord. So now it's both simultaneously a YouTube and Discord screen share, so I can show you what I mean. So you're gonna have this vector. Wow, looks more like a slug, and so there's gonna be a middle value, and you're gonna say I have middle value is gonna be that node, and then its left pointer is gonna be whatever calling the function on the left hand side. That's gonna give me back a node to some subtree. And its right-hand pointer is going to be whatever I call in the right half of the list. That's going to give me back a subtree on the right-hand side. And so because you're changing the pointers of that node in the vector, that means when you're done this whole process and you return back the root, all of its pointers and all of its descendants' pointers will be updated correctly. Does that make sense? Ish?
Yeah. Yes. But, okay, so... yes. But once you get that root node, to make the subtree, do you just... how do you make the subtree then to connect that left node?
Yes. How do you make the subtree? You make the subtree by recursively calling the function that you're in on the smaller, like the left sublist. So I'm in a function. This whole thing is like build tree from array or vector or whatever the hell you want to use, but vectors are easier. And that will take like some array as an argument, and it'll return back to you a node pointer.
Should we have like an array variable in the function itself that just holds a smaller and smaller part of the array?
Yeah, well, again, this is kind of like going back to, this is why people come out of 341 and they're like, oh, I understand recursion now. You're just implementing a function. You're just like, somebody gave me an array and they want me to make a tree out of it. So what I'm going to do is I'm going to take the middle node, and that's going to be my new root. Well, the first thing I'm going to do is there anything in the array? If there's nothing in the array, my node pointer is going to be null if there's nothing in the array, right? Because if there's nothing in the array, you want me to build a tree out of nothing? So you can't do that. Then what you're going to say is, okay, I'm going to take the middle node from this array of nodes. That's going to be what I return. But before I return it, I'm going to set its left-hand child to another recursive call to myself with a smaller array, that array being the front half of the array, and then I'm going to make my right child equal to calling build tree from array on the right side of the
shouldn't it take in like two arguments then? Because wouldn't your base case be the case that if you return a null pointer, like you're done?
No, because if that recursive call. The recursive call is giving me a node pointer back, and so if I make a call with an empty array and it gives me a null pointer back, then my left child should be a null pointer, so I just carry on. I don't even need a special case for that.
So you would just keep going until your array is essentially there's no... Oh, okay, I understand what you're saying now.
Yeah, so there's two cases. There's the case where you give me an empty array, at which point I say, I can't make a tree for you. The node pointer you want me to give you is going to be null. Have a nice day. The other case is, oh, there's something in this array. I'm going to take the middle item, the middle node from that array. I'm going to set its left child equal to a recursive call in the front half of the array, its right child equal to a recursive call on the right side of the array, and then return that root node back. And that turns out to be all that you have to take care of. It just kind of like Plinkos it out. Now, when you're debugging, you have to understand more in depth, like, because there's, you know, you're going to have indexes be off by 1 and stuff like that, but there's only really, it's actually not bad for recursion in terms of how many cases there are. There's 2 recursive calls, though. One for the new left subtree, and one for the new right subtree. Okay, cool. I don't know how to unmute Michael now that he's left. So, oops.
I was able to add a couple of consts to my functions in there for in-order traversal.
Okay, and did it...
And it doesn't like the fact that I'm putting the root in, because in the function I have a parameter that's taking the tree or the node that I want to do the recursion at, and it doesn't like the fact that it's in there. It has that outlined in red, saying non-const value reference to type const BST node. Can I bind a value of related BST node?
It probably means that argument has to be a const in the function that you're writing.
I have the argument being const in all of them.
So all of your arguments are const, and the method itself is const?
Yeah.
All right. Well, that's something you'll have to talk to somebody in a one-on-one session about, because I don't... It sounds like you're doing the right thing. But no, you can't take const off of dump.
I could probably just use a bunch of while loops. Less efficient, but it'll work.
Yeah. Actually, while loops are more efficient, but they're nightmarish to write. Because you won't stack overflow in a while loop.
Professor, just to double check, we don't have to edit our balancing function, right?
What?
Like, we don't have to change it? Like, the one that's given to us in the CPP file?
No, but you get a pointer to it. So, like, you're just calling it.
Okay, gotcha. Yeah, that's what I just want to make sure. That all that does is tell us if it's balanced or not.
That's correct. But when you're testing your code, you should give it a couple different balance functions and make sure it behaves. Muted you because I heard myself. Alright. Can you review what to test for? So, great question about how do we test things. The way that we test things is it's actually deserving of its own talk, and a couple of the TAs are going to give a separate session on how to write tests, especially for this project where we really, really want to see good tests. So they're going to be given a seminar on it. Feel free in Discord to give them feedback on like what you'd like to look at and so on and so forth for those. Any other questions from you guys in the voice chat? No? Somebody on mute?
Yeah, can you hear me?
Oh yeah, I can.
Oh, okay, awesome. I was wondering if we have to use a vector, because like I made an array for all the nodes that I visited.
You do not need to use a vector. A vector just ends up making your code a little bit easier. But if you use an array, congratulations, you did it the hard way.
Okay. Okay. Okay, yeah, I think that's it.
That's it? Great.
Yeah.
Alright, cool. Anything else? Oh, let me unserver mute Michael. Okay. Anybody else? Questions? Alright, good.
Just to double check though.
Yep.
when it's like when the project description says to use array balance, it's totally okay to use a vector.
Let me if we're talking in like, man, it's dog time here. When we're talking about what you are and are not allowed to use, I will double check. Oh, yes, you may not use vector. I apologize. You must use an array. You may not use any additional STL containers, and vector may only be used to store the string vector cars. So yeah, no, you have to rebuild from a vector. Thank you for reiterating. Gotta use an array, cannot use a vector. Which means you will probably have to send the size along with your rebuild from array function. You should send the size along as well as the array so that you know what to take half of to look in the middle. Okay. Any other questions? Or I'm going to call it a day. This is probably similar to how I'll be doing office hours next week. I've been super busy, but hopefully it'll be something akin to this. If you missed the front half of this on YouTube, you can rewind it. Also, it'll be available, I believe, immediately after I say that I'm done. So, alright, I'm going to stop streaming here, and then I'm going to stop streaming here.